Okay, I guess many audience from the AI talks are already here. And so today we are really happy to have Thaddäus here with us today, who is currently in his PhD, fourth year of his PhD, and currently doing an internship with Google DeepMind. So let me take the honor to introduce Thaddäus first, and then we will have Thaddäus introducing his latest work about reasoning and video generation for around 40 to 45 minutes. And then we will have a Q&A session right after the talk. So if we got any question at all to discuss with Thaddäus, you can raise your hand, type in the chat, or just unmute and join the discussion. So Thaddäus is a fourth-year PhD student in the International Max Planck Research School for Intelligent Systems and currently interning at Google DeepMind, Toronto. And most of Thaddäus' PhD focused on generalization, robustness, and benchmarking for large vision language, and video models. And his recent research investigates how generative video models can improve multimodal reasoning and how language model post-training can enable exploration beyond the pre-training data. So Thaddäus, please take over the time and let's have Thaddäus here.
Great. Thank you so much, Tsuchi, for the intro, and hi to everyone. It's a great honor to be here and present our latest work. I just shared my screen again. Can you see it?
Yeah, we can see it's perfect.
Okay, perfect. Yeah, so this is the paper on video models are zero-shot learners and reasoners. We published this roughly a month ago, and I want to take this talk to hopefully give also some, behind the scenes insights and sort of our thoughts behind this work that are not necessarily in the paper or on our project website. Of course, I should start this with the caveat that I am just presenting for the team that is really behind this. This was an amazing team. Especially shout out to my two supervisors in my internship, to Priyank and Robert. They had a lot of the initial ideas and it was super fun working with them. And also, I should highlight, I think at this point, I think I've seen some people online read this paper as sort of the VO3 release paper. And I just want to clarify again that this is very much not the VO3 paper. We're really just using the model that the amazing VO team produced. And we're, of course, showcasing some of its capabilities, but we didn't do any of the model training. We're just benchmarking. Yeah, so with that out of the way, I want to really show pretty much exactly what was going on in our heads as the motivation for doing this work. So we really started from this conviction that, at the moment, everybody is betting on LLMs being the path to AGI, hopefully at some point. Whereas video models, which are also, very expensive, powerful generative models, they're just really used to generate cute, pretty videos and maybe like AI slop. But I think it's not too far-fetched to imagine that, LLMs could be models for language understanding, and video models could almost mirror that exactly and be used as general purpose models for visual understanding. And these two types of models could really interact and hopefully like gain a lot from each other and could both together push us forwards towards some AGI future. And we really wanted to draw this parallel from LLMs to video models. So if we look at the sort of evolution or revolution that LLMs have gone through over the last decade, we really see that we started in NLP with a lot of specialized models for specialized tasks like summarization, translation, etc. And then started to build larger and larger models that maybe only have to be fine-tuned or like low rank adapted for specific tasks. But then at a certain scale, we realized, hey, these models we don't need to fine-tune them necessarily. They can work quite generally with just few-shot prompts or even with zero-shot prompts, right? And what this enabled is that suddenly we have one large model that can really do almost anything that has to do with language, right? Like it can do code, it can do creative writing, it can translate, reasoning, of course, and much, much more. But on the computer vision side, it feels like we're still a little bit stuck at those specialized models. So of course, these models have also been growing larger and more powerful. But if you look at something like SAM, that's an amazing model, but it's really just doing one very narrow task. And there's tons of models like that. And what we're really missing is this sort of generalist model. But a generalist model like that could, just like in language, also enable a lot of things under one unified umbrella, right? Like we could have a model that understands the 3D world. It can reason in space. It can know how physical dynamics unfold in the real world. It could manipulate or at least simulate manipulation in the real world. It could do anything that we're doing currently in image and video editing, be it like in painting or with masking or anything that we can imagine in this space. And my personal dream really is that we will go into a direction where we can even use these models for abstract visual thinking. So even if there's a task that on the surface is not visual, right, like some math or logical reasoning, I think as humans, we really tend to imagine things visually when we reason about problems. And it would be great if models would have this capability too. And I'm certain there are some tasks where this could be beneficial. So it would be really interesting to go in this direction. So this was the starting point. And really this slide here is one-to-one, one of the earliest slides we had in this project, where we just set out, we don't know how good models are at the moment, but it seems like video models might have the potential to become such general models. So let's see where we're at. Let's take VO2, take VO3, and just benchmark a couple tasks, see what the current state is. And so that's what we did. And I'm very happy to say, of course, that we found quite a lot of signals of some general visual intelligence. And it's quite exciting that video models that were not at all trained for these tasks still exhibit a broad range of tasks that they can solve. So we try to organize this breadth of different tasks that we tested and that we explore a little bit. And this organization is maybe roughly inspired by some knowledge about the visual stream in humans, but really it shouldn't be seen as a prescriptive taxonomy. Really, this is just us trying to organize these tasks a little bit to highlight some similarities and differences between different tasks. So on the far left here in blue, we have perception. We see this as the most fundamental ability. It's sort of a very passive intake of visual signals and roughly organizing them as you take them in. So this includes things like dealing with ambiguity, resolving noise in the input, and also having some simple biases like understanding objects and understanding contours. And on top of that, then, still a very passive process, but slightly more involved, is modeling. This can mean modeling the dynamics of the world, like physics. But this can also mean making a mental model of the world. So understanding relationships between multiple things in a scene, or having an abstract representation of a scene. Once we have sort of this passive model of the world, we can at least think about manipulating it, right? Like we can imagine what would it be like if a relationship between two things changed, or if one thing itself changed. And so that leads us to things like image editing and video editing, but also really to simulation of the real world. So simulation for robotics, for example, for complex manipulation tasks. But in my mind, these manipulation things are still quite short. So the time frame of this is still quite short. And they don't necessarily have a clearly defined goal in mind. As soon as we have a clearly defined goal and we have a long time frame and we string together many manipulation steps, that's when I would call it reasoning. We're trying to achieve a certain goal and we're trying to figure out how we get there from our current state. So with this overview, I now want to take the next, actually the bulk of this presentation, to walk through some examples in each of these categories, and just show what is working and give my ideas to that. So let's start with the perception. As I said, part of this means dealing with ambiguity and with noise. And it's probably not a surprise, given the training objective of denoising that diffusion models have, that video models can denoise quite successfully, right? They can deblur images, they can denoise them, they can remove different types of noise, even without knowing their distribution. And they can also perform this super resolution-like upscaling here from a pixelated image to the final image. So in all of the slides that I'm showing here, there will always be a video on the top left, and then I will show some successive frames, just so it's a bit easier to see what is the input and output. And I want to highlight again here that all the experiments we run are zero shot. So the model is really just fed this frame on the bottom left as the initial frame, and then a simple text prompt that I usually also include on the slides here. We can do more than just super resolution. So these models can also do low light enhancement, for example. Here we have a dark scene, barely anything is visible, and just prompting the model to turn on the light works quite well to produce a realistic scene. Another type of ambiguity that we have, like as humans, encountered quite often are sort of bistable images, like something like this, where it's initially quite unclear just seeing the white and black dots what this means, or maybe optical illusions. And to me, this all falls into a category of trying to understand what are the biases that the model has, right? Like if the model in these abstract shapes sees some other abstract shape that tells us something about what it tends to do. But it's quite remarkable, I think, that the model here in just these dots immediately, even without any text prompt, goes to complete a Dalmatian dog in this scene. So this tells us that there's some bias towards realism and some bias towards movement also in this scene. And there's a couple other sort of bistable images or optical illusions that we have looked at in this work. But I think there's much more work to be done in this space, looking at the biases that the models have through prompting them with illusions, for example. A maybe slightly more involved task is this key point localization here, where we prompt the model to put a dot on specific things in the scene and then fade the background to black while these dots start glowing. And I think this task, while relatively simple conceptually, also shows a sort of interesting thing that we need to think about, and that is, how do we want to phrase a given task visually, right? Like we could do key point localization by drawing a circle around a key point, or maybe you zoom in on a key point, or you do it like here and have a glowing marker. And we tried a bunch of these things, and usually what we report is what we found to work best. But this is by no means the best that's possible. So I think it will be quite interesting to see going forward what sort of interesting ways to phrase the same task people can come up with. And I'm sure there's a lot of performance to be gained just by prompt engineering, essentially. One other very classic perception problem is this conjunctive search, or like the binding problem. where a model needs to understand multiple attributes coming together. This was especially interesting for me because a lot of my early work has been on compositionality and generalization and combining different attributes. So it's quite nice to see that such a task that is hard for many embedding models was just working out of the box, where Veo can realize what is the shape, what is the color of an object, and where in the image is the combination of both. And of course, then we can move on to tasks that we can actually quantify. So the first sort of very classic low-level computer vision task is, of course, edge detection. And we can perform edge detection with Veo just by prompting it to trace the edges and then fading everything to white. And we end up with these edge maps that often are very, very surprisingly detailed even. So here's an example of the edge map on the left generated by Veo, and on the right, the ground truth for the same image. And we can see that Veo adds a lot of details, like the specific outlines of the foliage in the background or the tire threads that aren't even annotated in the ground truth because it would be super expensive to annotate this. So before I show like the quantitative results, I want to also give this as a like little remark that sometimes Veo suffers in the results because what it outputs is actually better than the ground truth. And before I fully show the results for this quantitative eval, I want to take a bit to contextualize what these results mean. So for all of the experiments we're doing, we're showing the performance of a model over multiple attempts. So on the left with just one attempt, and on the right with up to 10 attempts. And we do this for both Veo2 and Veo3. So we can read multiple things from these plots. The first thing, if we just take like the maximum of these curves, is just what is sort of the best performance we can get out of this model at the moment. So this is sort of the ability that the model has to solve a task. But the increase from the starting point at like 1 attempt to 10 attempts also tells us something about the reliability of the model. So for some tasks, we will see this curve is rather flat, and the model just has maybe not the perfect ability, but it solves this task very reliably. But for other tasks, we really see that the model, there's a huge difference, which means that while the model in principle can solve the task, often other things like some hallucinations or other glitches get in the way. And I think this then always is a signal to us that, hey, the model has this ability in principle. Probably in the couple next model iterations, we can expect a large performance gain here. And the last thing we can read from these plots is the difference between Veo2 and Veo3. And to me, that's almost the most interesting because these two models came out with like roughly 6 months time difference. And so when this gap is large, and it's often quite large, this really means that progress here is extremely fast. And probably the next couple iterations of models, and not only in the Veo family, also from other labs, will make big strides on a lot of these tasks. Okay, so now that we understand what the results look like, here are the results for edge detection. And so on the left, we're reporting performance on the best frame, and on the right, just on the last frame, just as a fixed reference. Here, the performance is quite similar on both, but for a lot of the tasks later, we'll see that this makes a big difference. And what we're measuring here is sort of the quality of the edge map, where 1 would be perfect. And we see a couple things. First, as I said, the performance gap between Veo2 and Veo3, so between the blue and the red, is very significant. So we can hope for much faster progress here also in the next couple of years. The other cool thing that we see here is we're comparing to the performance of NanoBanana. And NanoBanana, which is the Gemini image understanding checkpoint, is of course an image-to-image model. And the edge detection task, how we formulated it, is an image-to-image task. So it would not be unreasonable to believe that Nano Banana might perform much better because it doesn't have to, go through this extra computation, and it has specifically been trained for image-to-image tasks. But what we see is actually that Veo matches or outperforms Nano Banana. So this is a really, really strong and cool result for us that shows that, yeah, video models really have this sort of general ability that we're looking for. And of course, I should caveat all of this with saying that this is, of course, below state-of-the-art performance. Like on this data set, state-of-the-art would maybe be around 90 or 95%. But it's still amazing to see this progress and to see that Veo can beat Nano Banana. With that, I want to jump to another low-level vision task, which is segmentation. So here we just tell the model to fade the background to either white or green, and then color each object that it sees in a different color. So this is maybe a bit different from something like SAM. We're not specifying which objects we want to segment. There's no like key point, or we're not mentioning any object in the prompt. We're just saying anything that's conceivably an object, just give it a different color. And here we also see something interesting already in this example. Initially, the sheep are colored differently in red and blue, but then as the task is fulfilled, but Veo still has like 1 second to fill up, it just needs to modify something. It has this really strong bias to keep going. So then it turns one of the sheep red. So this is a good example where we see that can make a difference whether we evaluate on the best frame, which would here be a perfect segmentation, or on the last frame where Veo went off and changed something unnecessarily. And another thing I want to highlight here is that we take the original images and we pad them. And when we're padding them, we're doing it with the same color that we specify in the prompt. This makes a lot of sense, but this is a very, very simple example of sort of a visual prompt engineering. Because the prompt is, of course, the text, but also the starting frame. And so how exactly we set up the starting frame also impacts performance. And I think I'm extremely curious to see in the next couple of months what other people can come up with on the visual prompt engineering side, because I think this area is completely underexplored and can be very promising. Yeah, so here are the results for that. Again, we see a large difference between Veo 3 in red and Veo 2 in blue. So again, a large progress within just 6 months. And again, at least if we're looking at the best frame performance, Veo, which hasn't been trained for this and for this image-to-image task, matches the performance of Nano Banana, which is super cool to see. But there's another interesting thing here that I want to point out, and that is we tried the same task here with both a green background and a white background. And the green background performance is the solid line, and the white background is the dashed line. And so what we're seeing here that is that green just performs better. The green background for Veo 3 performs much, much better than the white background. And we don't have a perfect explanation for this, but my assumption is that there's a lot of data online, like videos, that probably does chroma keying, like recording something on a green screen. And that is probably much more common than segmenting things on a white background. So I assume that that plays a big role, like what is the data distribution like in what the final performance is and what prompts work well or not. So again, this is sort of a point about prompt engineering, that just by changing this one word in the prompt and changing the visual prompt, we can get this performance gain. Yeah, so with that, let's jump ahead to the modeling section and look at some examples there. The first thing, of course, is sort of physics understanding. And we have included some of these examples in the paper, but honestly, there's a lot of great benchmarks for physics understanding and world modeling already out there. So we didn't feel like this is the most important point that we make. I think people understand that video models are promising for sort of simulating the physical world. Nevertheless, it's quite cool to see that, for example, here, the material optics are done simulated quite well. Veo either puts reflections on this mirror polish metal sphere or inverts the image through this glass sphere. I'm just noticing the labels here are swapped. But nevertheless, it's quite cool to see that Veo can do this quite reliably. Another nice demonstration of this is this buoyancy test, where we just specify that a hand lets go of an object and the rock sinks as is expected, while the bottle cap floats. And we have a bunch of other sort of demonstrations of physical properties in the paper or on the website. But I want to move on to more abstract relations, because I think this is a very, very important part of modeling the world. So here's a maybe slightly constructed example of a visual memory, where after zooming in, it's not clear that when you zoom out again, you can remember the whole world state. So the different colors of the different houses in the correct order. For example, there's a little bird on one of the chimneys. And so it's maybe not surprising that on this short time scale that these videos are, like 8 seconds, Veo can remember the world state. But I think this is a very important thing to keep in mind, that memory of the world state is very fundamental for a lot of more complex tasks. So it's nice to see this signal here that this is possible. Another abstract relation is part-whole relationships. And parsing larger things into individual parts also has been a long-standing problem in computer vision. And so, for example, this is from the Omniglot paper that specifically benchmarks for this. And so this is just one example. And here, Veo sort of implicitly parses the character on the left into its individual strokes just by drawing them out one by one. And so just this like parsing by assembly or by disassembly, I think can be quite a powerful way to look at interactions between objects. Lastly, I have here an example of novel category learning. So here the task is to identify in the grid on the left the object or the symbol here that belongs to the same category as the example on the right. And what's really interesting in this task is that Veo can get it right quite consistently. But as I said earlier, Veo has this strong bias to just keep things moving. If it solves the task by 6 seconds, but it still has 2 seconds of generation left, something needs to happen. So that's quite unfortunate, because often it means it finds the correct solution, but then messes it up again. So here we have this trick that we used a couple times, where we tell the model to, once it's done, show a color wheel that's also spinning. So the spinning means that the model has something to do, and it can sort of focus on isolating the movement there. And the color wheel, the appearance of that, is a good marker for us when we should evaluate. So we evaluate the frame in which the color wheel appears, and that gives us sort of a fair way to evaluate and gives the model a way to signal the task is done now. Yeah, let's move on to the next section, manipulation. So the biggest category here is, of course, image editing. And I think the most fun way to do that, as we discovered, is by doodling. So you just annotate in the image what you want to change, and then just tell Veo to let that happen instantly. And this was so successful. I think this is now part of the Veo online, like in Flow. I think you can now edit images and scenes with this. Of course, there's a lot of other ways to edit images, and I think in general, Veo is just quite good at these. So you can compose objects into a scene, you can do in and out painting, you can do style transfer, you can manipulate text, and videos of all of that are on the website. But I think this is sort of one general category, and you get the idea. But I want to highlight one aspect of this, and that's sort of the 3D awareness in image editing. So classic image models, image editing models, they have to produce the final output in one step. And when doing that, it's quite hard to maintain consistency, like all the textures and all the details stay the same. And it's also hard to know, what is physically plausible, right? Like, can one object move through another or not? Like, how can a character move their limbs in a plausible way? And I think this is an area where video models can be really, really powerful, because you just break up this large image editing task into a lot of small steps that are quite easy individually. And this usually yields results that are quite faithful to the original and quite good looking. And so this is also visible here in this novel view synthesis. We can just rotate the camera to get a novel view of the statue. And in the background, sort of the building changes plausibly with the camera movement as well. We also briefly benchmark this a little bit. So we just did human evals of some samples. And in general, VO3 is just amazing here. When the fidelity, so just the ability to do the correct edit, is 100%. It does great edits. The precision is sometimes not so amazing. So often Veo will also introduce other changes in the background somewhere, for example. But still, the performance gap here to Veo 2 is quite large. So I'm sure that the next iterations of models will do much better here. And again, this is a nice example where you can see that a lot of the detail is preserved, because all of this texture of this thick coat of paint on this rough metal surface is perfectly preserved as the color changes. So manipulation then, I think the more interesting part than just image and video editing is actually the ability to simulate things. Because I think if you ask a human to do a certain task, there's often sort of this visual process going on where you think, these are the steps I would do in some certain way. And I think this can be quite powerful for simulating, for example, robotics, or simulating training data, training maybe VLAs or other models that can benefit from this data. And we can see that the fidelity here is quite nice. So the model pretty well adheres to the plausible motions and movement of these robot arms, and it holds the jar while it unscrews the lid in quite a physically plausible way. So this was super cool to see that this works. So as a takeaway after these first three categories of tasks, I think it's quite clear that video models can solve a very broad array of tasks in just a zero-shot manner. And while the performance is often still under state of the art, I think it's also quite clear that in the next couple of years, we will see video models that will match the performance of bespoke models and maybe even supersede them. And yeah, I think it's clear that the trajectory here is really towards these general foundation models for vision. That is, of course, once we figure out how to make them a bit cheaper and have longer generations and so on. So lastly, I want to look at the reasoning category, which is, of course, the most exciting, I think. And to me, this is something that's super interesting, because there's a lot of works on visual reasoning, but usually visual reasoning really means the input is visual, and then the entire reasoning is just happening in language space. I'm really, really hoping this we can sort of slowly push into a direction where some of the reasoning also happens visually in the vision modality. Because I think for humans, it's quite clear that for some tasks, it is easier to reason about them visually and just imagine, tracing a path or like seeing visually how some things connect, than phrasing everything in language. So this is just a small sort of inspiration for this direction, but it's very, very cool to me. So here in this task, the question was what containers will fill up and in what order. And it's maybe a bit small on the screen, but some of these containers are closed off because the pipes are closed at the start or at the end. And Veo can sort of simulate this water flow and fills the containers in just the correct order. That's quite nice. And I think we tested this at the time with Gemini, and Gemini didn't solve it. So this was also a nice moment for us. And I think we can sort of transfer the same idea to more abstract things, right? I mentioned in the beginning that I would really like to see visual reasoning for like just abstract math or logic puzzles. And we could, for example, imagine that we make a graph of our problem, but then like traversing this graph could be maybe easier visually with some flood fill algorithm like here than in language. I don't know, it remains to be seen, but it's definitely an interesting direction. We also looked at sort of some reasoning challenges that you would maybe pose to an animal, right? Like there's a lot of these experiments with crows, for example, where they have to use a proper tool to reach some food. And so here, the model has a hammer and these tongs, and just telling the model that the person retrieves the walnut, Veo simulates a correct use of the correct tool to retrieve the nut, which was amazing to see. One of the most interesting examples is definitely this one. This is some rule extrapolation inspired by ArcAGI, the first split of ArcAGI. And so the task here was to fill in the grid on the lower right to complete the pattern. Again, Veo here was a bit doing a bit too much and also solving in the other grids. But if we focus on the grid on the lower right, we can see that Veo filled this in absolutely correctly. And this is super cool that this is working out of the box, zero shot, without ever having trained for that. So now we come to the tasks where we actually ran some quantitative analysis. So the first one was visual analogies. So how does A relates to B, like C relates to question mark, and the model has to fill that in. And here we saw that Veo 3, again, performs much better than Veo 2. And on some analogies, when the color changes or the thing is resized, Veo 3 reaches reasonable performance. But we also saw that always on reflections and rotations, the model is really, really poor. And this is sort of a failure case that we saw also in other tasks, that somehow reflection and rotation of objects is very hard for the model. I have no explanation for it, but this is definitely something that should be looked into further. Then we had the visual symmetry, just completing a pattern or shape. And this one also, I think this is one of the task with the biggest performance difference between Veo 2 and Veo 3. Veo 3 does absolutely amazing here and completely blows Nano Banana, which again is an image editing model that might reasonably be expected to solve this task. It completely blows that out of the water. So with that, we come to the last reasoning task. This one was super, super fun, and it really was just started by this crazy idea. Hey, maybe the model can solve a maze if we just put cheese on one end and a mouse on the other. And we were super surprised that this actually worked. So we sort of formalized it a bit more and tested it with a set of abstract mazes. And here we tested sort of an array of mazes of different difficulties and ended also with mazes that are irregular. So they're very hard to ask a language model about because there's no specific grid. You can't represent them in ASCII easily and so on. So what we see here is that, again, Veo 3 in red performs much better than Veo 2. And if we compare to Nano Banana, we see, at least on the easier mazes, Veo 3 again matches or outperforms Nano Banana. But on the harder mazes here, Nano Banana does actually better. And I think the reasoning for that is that the generation length is still very constrained with 8 seconds. So if the path is too long, which happens quite frequently in the larger mazes, Veo doesn't complete it in time, whereas Nano Banana can still draw a complete path. So I think as generation length increases, we'll also see models getting better here. But what's even more interesting is that if you compare it to Gemini, the dotted line is sort of Gemini if you give it a text representation of the maze. And the dashed line is Gemini if you give it an image. And Veo just does much better than Gemini. And for the largest mazes, it even beats Gemini on a text description. I think this is super surprising. And this is really a signal to me that there is some place for visual reasoning in reasoning tasks. Yeah, and you can also translate this to the real world. Here's an image of a very simple maze with a robot. And so you can imagine how this could be used for actual robot planning and navigation. Okay, so the takeaway here is that really we can think of models as solving these complex visual tasks just step by step in a series of frames. And so that's why we call it sort of chain of frames to mirror the chain of thought reasoning that we have in language models. Okay, I have a very short section here on some failure cases because I don't want to give the impression that Veo solves everything. And I try to group these a little bit into related things. So I said that Veo struggles really with like transforming objects plausibly, like rotating them, mirroring them. And we see this here, for example, moving the couch from one room to another. Instead of rotating it to fit through the gap, it's just being deformed weirdly. The same happens with these colliding balls and with this vase. I think some work still needs to be done. Veo is not a physics simulator yet. It's also striking. There's definitely some tasks that's just too complex. And maybe that's because they're just inherently complex to simulate, like this folding of a garment. But I think it's also sometimes the case that it's just very complex to describe how to solve a task and verbalize what you even want. So for this depth estimation and surface normal estimation, it was very hard to describe to the model what we want, and we never got this to work. And lastly, I think this is a sort of task that I care a lot about because I think it's a great example for visual reasoning, which is puzzles. I had hoped that this would work out of the box and Veo could unscramble an image or solve a sliding puzzle. But again, sort of the inability to move an abstract shape while keeping it fixed in its appearance also was a problem here. So even in the puzzle where it can select the correct piece, it doesn't rotate that piece, for example. So I want to end on some of the lessons we learned from this, because I think these failure cases are, of course, a bit sad, but it's also a great point to learn what worked. And I think we went through a lot of failure cases internally before we found so many cool examples. And so the first thing is just to be precise, remove ambiguity, and also specify what shouldn't change, because it's often easy to think about what we want, but verbalizing it is hard. The second is this sort of thing I showed with the spinning color wheel, where Veo just has this bias to keep things moving in the scene. And sometimes that messes things up. So having an outlet can be helpful. Then, as I said, there's this, I think this will be a new sort of area for a lot of creativity in the field, visual prompt engineering. We have seen a lot of papers on prompt engineering, and I think with video models, a lot of performance can be gained, and maybe some of the tasks that we weren't able to solve can be solved with better visual prompts. And lastly, one form of visual prompt engineering that we found very useful is to aim for realism. So that can mean having an abstract task and using Nano Banana to render it as a realistic scene can help to make the task work. Yeah, that's everything. There's a ton of the videos if you want to go through them in your own time on our webpage. And thanks to everyone who helped out with this project. Yeah, thank you.